Introduction to Galileo. Galileo was born in Pisa, Italy on February 15, 1564. His father was a musician. Galileo's mother was Giulia degli Amanati. Galileo was the first of 6 children. His family belonged to the nobility but was not rich. In the early 1570s, he and his family moved to Florence. Galileo was never married, but he had 3 children with Marina and Venice. What is he known for? Galileo's law of motion made from his measurements that all bodies accelerate at the same rate regardless of their mass or size, paved the way for the codification of classical mechanics by Isaac Newton. Galileo's heliocentrism with modifications by Kepler soon became accepted scientific fact. His invention from compasses and balances to improve telescopes and microscopes revolutionized astronomy and biology. Galileo inclined planes. In 1603, Galileo used his inclined plane, a simple board with a groove, which he rolled a small metal ball to examine Aristotelian idea about motion. Galileo inclined plane experiment radically changed these ideas by concentrating on acceleration, a stage of motion ignored by Aristotle and most of his followers. Galileo hypothesized that a falling object will gain equal amount of velocity in equal amount of time. Galileo discovered through his experiment that the objects fell with the same acceleration, proving his predictions true, while at the same time disproving Aristotle's theory of gravity, which states that objects fall at speed proportional to their mass. As Galileo discovered, from 1 second to the next, as the ball rolls down the inclined plane, the ratio of distances covered increased by odd numbers, by intervals of 1, 3, 5, 7, 9, etc. What did Galileo use to measure time? Galileo accurately measured these short periods of time by creating a pulsillogon. This was the machine created to measure time using a pendulum. The pendulum was synchronized to the human pulse. He used this to measure the time at which the weighted balls passed marks that he had made on the inclined plane.
To recreate Galileo's project, we took a 2x4 piece of plywood and added pieces of more plywood to the edge to create a linear groove to roll a marble down. We then used a bucket to create a water clock where we put a hole in the bucket and used a straw and a binder clamp to slowly put water through. We rolled the marble down at the same time releasing water and estimated the time. To recreate Galileo's project, we used a piece of plywood and created a groove in the middle of the plywood to roll a marble down. We then inclined to using another piece of plywood. To make the water clock, we used a bucket and put a 1/4 inch diameter hole in and inserted a straw. We then held the straw up to stop water flow, and when the marble was dropped, we moved the straw down to let water out into a small beaker. We then used that beaker and a scale to measure the amount of water, which we then turned into increments of time. This is a video we took of our experiment, and this is how we got our increments of time.
Jack called start.
Ready, go.
Stop. We're just going to take this beaker, going to draw out the side from the bottom. We're going to wait. Oh.
Here you go, and I'm not going to question it.
As you can see in the video, we dried the beaker off with washcloths to make sure that we got accurate measurements. And we proceeded to do this 10 times at measurements of full length of the board, 3/4 of the board, half of the board, and 1/4 of the board to get averages throughout the experiment.
What does our data look like? First, we weighed our beaker, which was 58.7 grams. Then we weighed the water with the beaker from the time the marble came from the top of the ramp to the bottom of the ramp. The data we got from the table on the left, we subtracted from the weight of the beaker, able to get just the weight of the water by itself. For each test, 1 through 10, we were able to find the average. Using the averages, we then found the standard deviations of time. The full length equals 3.422, 3/4 2.728, 1/2 3.752, 1/4 2.428. The length and time ratios. At first, we find our time ratio of 0.498, 0.659, 0.877, etc. How we found these was we did 1/4 16.21 divided by our full length for the first one, and at the second one, 1/2, we did 21.46 divided by 32.55, etc. to make these length ratios. We used our averages to find the time ratios. With the time ratios, we then square them, cube them, and also square root of them, giving us our graphs. First one is our time ratio. As shown, it does not make a linear graph. It's a quadratic, that's upside down. Our second graph is the square root time and length ratio, time ratio, excuse me. And as you can see, it is also not a linear graph. Moving on to our squared time ratio, you can see that it is a linear graph with a slope of 1.021. The y-intercept is super close to 0, which guarantees that this is a linear graph. If it was too far slope, our y-intercept was going to be anything other than 0, it would be inaccurate, and just wouldn't make sense. Last, this is the cubed time ratio. As you can see, is not linear and therefore irrelevant.
All right, and in this last part, we compare our conclusions to the equation we ultimately got from our squared time graph versus the ratio of length. Galileo used an incline plane and a water clock to show that it took a ball. When a ball moves down an inclined plane, it was not directly proportional to the distance it traveled, like Aristotle claimed. Instead, for every unit of time that passed, it moved in increasing lengths of 1, 3, 5, 6, 5, 7, and 9, on and odd numbers. However, this begins to break down because the process is actually exponential. The ratio of time squared is equal to 1.021 of the length ratio. We only had a deviation of 0.021, and this could easily be accounted for by friction or experimental error. Ultimately, we got really close. That's all we have for today. Jack presented the entirety of the introduction. Brandon provided all the information on the lab experiment, and Ramon provided all the commentary on the tables and the graphs. Thank you for your time.